in general, my interest is in uncertainty and its kind of propagation. And of course, if you have, for example, a probabilistic uncertainty on the inputs, there are known ways to propagate it. If you have interval uncertainty on the inputs, you can propagate it. If you have expert uncertainty described by fuzzy logic, you can propagate it. The problem becomes, and this is a challenge which many people are working on, me includingly, is what to do if you have different types of input with different types of uncertainty. For example, some values come from measurements and they come with known probabilistic uncertainty. For some, we only know the upper bound of the measurement error. That's the interval uncertainty. Some come from expert estimates. How do you quantify the results? And that's very important in many practical problems. For example, if you are solving big challenges like estimating the risk of global warming or whatever it is, that's exactly the case. Some values come from measurements, some values come from expert estimates, and how do you combine this uncertainty together in a reliable way? That's not clear, and that's a big challenge. My thinking is the main challenge is to come up with reliable and kind of acceptable methods for dealing with uncertainty. Because, again, many of these issues are political. So, for example, same thing like global warming. There are many different ways of handling uncertainty. Some lead to higher values, some lead to lower values. If you are an alarmist, if you want to kind of increase the people's concern, you use the methods which lead to higher uncertainty, to higher values. If you are more conservative, you think no, that won't happen, then use other values, and it becomes political struggle. It shouldn't be a political struggle, and of course, there should be some objective way. Like same things happened with probability until probably 16th or 17th century. Probability was like uncertainty now. Everybody has some ideas. People were gambling, people were just doing some predictions, but there was no precise techniques on probability until scientists came up with some general ideas. And there's still, of course, some arguments between themselves. There are different camps in probability approaches, but still more or less things are settled. And I think what we need to do is we need similar settling in all other types of uncertainty, especially uncertainty related to kind of fuzzy and other stuff. And I think that's the main future direction, because people look to science as an arbiter. Because of course, okay, president says something, an actor says something, it's good, it raises emotion, but then the next thing is we need to analyze. So how important is it? How will the temperature rise at the end of the century? By 1 degree, by 2 degrees, by 3 degrees? What do we need to do? And science, unfortunately, is not yet giving them convincing answers, because there are many groups, they give different answers, and it would be nice to have to come up, and it's a research question. We need to come up with the technique that will enable us to provide answers which are convincing. Like, for example, you don't argue if you want to send spaceship to the moon, you don't argue. You just do the calculations. The only argument can be whether we fund this program or not. But in other programs, it's not about funding, it's about arguing. And that's because, of course, when you go to the moon, first time people went to the moon, it was almost like that. People were not even sure. When the first astronauts went into space, people were not even sure that they will not die out of radiation or something. But now we know that. Now we have a lot of measurements. We can use the equations to predict. For other issues, it's more difficult. And I think that's the most important challenge to our research community. I think I can detect that. So what happened is I was a student in the mathematics department, but I always liked applications, especially applications like in space-time and everything. And I started working in the Special Astrophysical Observatory in Russia. where we analyzed the data from the radio telescopes. And it's a very challenging thing, because at one point, I remember at one of the conferences, just to attract people, they had an exhibit on radio astronomy, which consisted of the table on which lay blank sheets of paper. And on each sheet of paper, it says, turn me over. So when you turn it over, it says, when you turn it over, you use more energy than all the radio telescopes have collected throughout the whole history of radio astronomy. So these are very weak signals. So when you are dealing with distance from, I don't know, Chian to El Paso, you can measure it approximately with accuracy 1 kilometer. Using GPS, you may get accuracy 1 meter, but it's a minor thing. It's not a big deal. It's exciting to know that, well, maybe if you kind of planning to deliver with the robot some gifts, that's a different thing. But if you're just traveling by plane, it's no big deal. But if you are dealing with signals from radio telescope, where we are dealing with measurements on the edge of accuracy. So if you don't deal precisely, if you don't deal accurately, you will never know what is the signal and what is actually noise. And that's a big issue. And you need to be very careful about that, because you may think that this is a signal, but in reality it's noise, and vice versa. And this kind of caused me to become serious, to learn all these techniques and to see that there are many challenges in addition to these techniques. Because one of the challenges was that if you deal with normal measuring instruments, you can calibrate them by many times kind of measuring the same thing, comparing with some standard instrument. But when you have state-of-the-art telescope, there is no more accurate standard telescope to compare it with. And of course, you cannot calibrate, so you have to rely on some theoretical bounds and everything. And I think that was when I really understood that there is a big need in many application areas, especially in state-of-the-art physics and state-of-the-art developments, to take uncertainty into account. We have some ideas on which we're working with one of my students, and the idea is related to the third applications, because one of the things that we mentioned is that one of the uses of green computing is that we can actually use, instead of just computing everything from scratch, we can use observations of physical world to help computations. Because in the real physical world, there are many processes, and sometimes instead of simulating them on the computer, you just look for them. For example, I don't know if you, no, maybe not bad example from the environmental viewpoint, but if you want some exponential dependence, you can just take radioactive material and measure how it decreases with time instead of doing the calculations. And of course, this is not a very good example because it's not saving too much time, but there are many other examples. And what I cited a paper in that long paper is that in almost all cases, in some reasonable sense, use of physical devices physical processes can speed up computations. Now, it turns out there have been some progress in this area, and we are working on that, because it turns out that people have been analyzing it from the viewpoint of theoretical computations. There is a special notion of kind of weak sequences, which means that a sequence for which does not lead to more than polynomial speed up in all the computations. It turns out, and that was a big challenge, which was resolved a few years ago, that they found that there are such sequences. But the very fact that it was so difficult to find these sequences can be turned around. From the viewpoint of using these sequences for computation, it's the other way around. It means that practically all sequences, not just almost all, but practically all, have the property that for some computations, they provide a very serious speed up, more than polynomial. And that's kind of what we're trying to explore now in our research. That's a very good question, and thanks for asking. my viewpoint is that what I'm trying to do, first of all, students are helpful. Of course, without students, it would be very difficult for me to, to do research. That's a big advantage of the university. You have a lot of young, enthusiastic, talented folks who are willing to help. How is this related to teaching? It's also very straightforward, because how do you motivate? How was I motivated to study? You go into whatever discipline you go in, for example, computer science. You want to do something specific, and you are not realizing, most often young people don't realize that in order to do that, you need to know a lot of other materials. So you need to know a lot of mathematics, you need to know statistics, calculus, you need to know some ways of communicate, you need to know what, in our case, English, in your case, probably Chinese, and how to do that. And there needs to be some motivation. So what I'm trying to do in my classes is encourage students to, especially in upper level classes, to participate in research. So what I do is, for example, in the classes, a big portion of the grade comes from the project. And the project is either, if a student is already working on research, then that student needs to relate that research topic to what we're studying in the class. If the student is not working or there is no relation, then I try to give them some research topics where, with the help of graduate students, they can do something. And that's very good incentive, because students get an idea that this can bring them to kind of to increase the amount of knowledge in the world. And this also is good for their egos, because everybody likes to praise athletes. If you have a world record, that's it. You are like all over the news. But in science, every publication, in effect, if it's not a survey, it means doing something that was never done before. So it is a world record. So if a student has 2 papers, that means he has 2 world records. This is a good boost for their ego, and that kind of encourages them to study better. Because whenever you teach classes, even a student likes computer science, that student may want to do, I don't know, machine learning. Great. But in order to do machine learning, in order to do serious research in machine learning, you need to know mathematics, you need to know calculus, you need to know linear algebra, you need to know all this stuff at least. And of course, you need to know a lot of things. And when you start doing research, you realize that. So it's not, all these classes are not what kind of professors require to you because they don't know better, but they are really important and really useful. And that's, I think, the way to make students study better and to make them more motivated to study. So in the ideal world, I think everybody should be doing some research. It doesn't mean that all the students will be Einsteins and just come up with great ideas and get PhDs, but if at least participate, at least start with something. Like, not just, for example, like you mentioned the robots or whatever it is. Well, everybody loves to do work with robots, but when you work with robots, instead of just repeating, which is a little bit boring, what was the assignment, try some experiments. And if you have some good leadership, good mentorship, there is a big chance that, especially if you're not on your own, if you're in a group, that somebody may come with an interesting idea that may eventually lead to some interesting results and even publication. So I think there is no big contradiction between that. So research is a way to teach better. And of course, teaching is a way to kind of encourage students to research. We all do that. Like in every class we teach, we are trying to kind of, even if it's a low level class, starting introductory class, we are trying to kind of pick up students who are doing well and kind of try to give them some challenging issues. And sometimes students succeed. Well, if it was only one sentence, I would repeat the same thing that when I became a student, one of our professors, Professor Smirnov, told us. That sentence is very straightforward. If you have some idea, drop everything and write it down. Because in a week or two, you'll forget it and it will take more time for you to recall. That's the advice I'm trying to follow. That's the advice I give to my students. And that's the advice I will give to any students.